What do we know about the universe, and how do we know it? Where did the universe come from, and where is it going? Did the universe have a beginning, and if so, what happened before then? What is the nature of time? Will it ever come to an end? Can we go back in time? Someday the answers to these may seem as obvious to us as the Earth orbiting the Sun. Only time will tell. As long ago as 340 BC, the Greek philosopher Aristotle, in his book On the Heavens, was able to put forward two good arguments for believing that the Earth was a round sphere rather than a flat plate. First, he realized that eclipses of the moon were caused by the Earth coming between the Sun and the moon. The Earth's shadow on the moon was always round, which would be true only if the Earth was spherical. Second, the Greeks knew from their travels that the North Star appeared lower in the sky when viewed in the south than it did in more northerly regions. Aristotle thought the Earth was stationary and that the Sun, the Moon, the planets, and the stars moved in circular orbits about the Earth. He believed this because he felt, for mystical reasons, that the Earth was the center of the universe, and that circular motion was the most perfect. This idea was elaborated by Ptolemy in the 2nd century AD into a complete cosmological model. The Earth stood at the center, surrounded by 8 spheres that carried the Moon, the Sun, the stars, and the 5 planets known at the time: Mercury, Venus, Mars, Jupiter, and Saturn. Ptolemy's model provided a reasonably accurate system for predicting the positions of heavenly bodies in the sky. But it had some flaws too. A simpler model, however, was proposed in 1514 by a Polish priest, Nicholas Copernicus. His idea was that the Sun was stationary at the center and that the Earth and the planets moved in circular orbits around the Sun. The death blow to the Aristotelian theory came in 1609. In that year, Galileo started observing the night sky with a telescope, which had just been invented. When he looked at the planet Jupiter, Galileo found that it was accompanied by several small satellites or moons that orbited around it. This implied that everything did not have to orbit directly around the Earth, as Aristotle and Ptolemy had thought. At the same time, Johannes Kepler had modified Copernicus's theory, suggesting that the planets moved not in circles but in ellipses. The predictions now finally matched the observations. In 1687, Sir Isaac Newton published his Philosophiae Naturalis Principia Mathematica, probably the most important single work ever published in the physical sciences. In it, Newton not only put forward a theory of how bodies move in space and time, but he also developed the complicated mathematics needed to analyze those motions. In addition, Newton postulated a law of universal gravitation, according to which each body in the universe was attracted toward every other body. It was this same force that caused objects to fall to the ground. Newton realized that, according to his theory of gravity, the stars should attract each other, so it seemed they could not remain essentially motionless. Would they not all fall together at some point? Newton argued that this would happen if there were only a finite number of stars distributed over a finite region of space. But he reasoned that if there were an infinite number of stars, this would not happen, because there would not be any central point for them to fall to. In an infinite universe, every point can be regarded as the center, because every point has an infinite number of stars on each side of it. Now consider the finite situation, and ask how things change if one adds more stars roughly uniformly distributed outside this region. According to Newton's law, the extra stars would make no difference at all to the original ones on average, so the stars would fall in just as fast. We can add as many stars as we like, but they will still always collapse in on themselves. We now know it is impossible to have an infinite static model of the universe in which gravity is always attractive. Those who realized that Newton's theory of gravity showed that the universe could not be static, attempted to modify the theory by making the gravitational force repulsive at very large distances. It allowed an infinite distribution of stars to remain in equilibrium, with the attractive forces between nearby stars balanced by the repulsive forces from those that were farther away. Another objection to an infinite static universe is normally ascribed to the German philosopher Heinrich Olbers. The difficulty is that, in an infinite static universe, nearly every line of sight would end on the surface of a star. Thus one would expect that the whole sky would be as bright as the sun, even at night. Olbers' counterargument was that the light from distant stars would be dimmed by absorption, by intervening matter. However, if that happened, the intervening matter would eventually heat up until it glowed as brightly as the stars. The only way of avoiding the conclusion that the whole of the night sky should be as bright as the surface of the sun would be to assume that the stars had not been shining forever, but had turned on at some finite time in the past. In that case, the absorbing matter might not have heated up yet, or the light from distant stars might not yet have reached us. When most people believed in an essentially static and unchanging universe, the question of whether or not it had a beginning was really one of metaphysics or theology. But in 1929, Edwin Hubble made the landmark observation that wherever you look, distant galaxies are moving rapidly away from us. The universe is expanding. Hubble's observations suggested that there was a time, called the Big Bang, when the universe was infinitesimally small and infinitely dense. Under such conditions, all the laws of science, and therefore all ability to predict the future, would break down. The eventual goal of science is to provide a single theory that describes the whole universe. It turns out to be very difficult to devise a theory to describe the universe all in one go. Today's scientists describe the universe in terms of two basic partial theories, the general theory of relativity and quantum mechanics. They are the great intellectual achievements of the first half of 20th century. The general theory of relativity describes the force of gravity and the large-scale structure of the universe. Quantum mechanics, on the other hand, deals with phenomena on extremely small scales. However, these two theories are known to be inconsistent with each other. They cannot both be correct. One of the major endeavors in physics today is the search for a new theory that will incorporate them both, a quantum theory of gravity. We do not yet have such a theory, and we may still be a long way from having one, but we do already know many of the properties that it must have. Ever since the dawn of civilization, people have craved for an understanding of the underlying order in the world. Today we still yearn to know why we are here, and where we came from. Humanity's deepest desire for knowledge is justification enough for our continuing quest. And our goal is nothing less than a complete description of the universe we live in.